Loughborough is a collection of 8 leading universities in the UK brought together in a research program. But one of our other missions is to create a community in the UK, including industry, academics, and finance, etc. All of those who are interested in research and development. So we have a leaflet here. You can join the network by a couple of clicks, and there are some of these leaflets in the room adjacent to this, so please join. A couple of things we do is that we do organise events which include commercialisation of solar technologies, and we have a business and industry showcase which is free to anybody. So what I would like to do is just introduce the range of different technologies that are now available to produce power from the sunlight, give you a history of what's been happening in the marketplace, and perhaps explains why the cost of panels has reduced so dramatically, and then point out maybe a couple of success stories that are occurring right now in the UK. So this graph here is the increase in module production against year, and this is 2000 to 2012. And each one of these bars here represents the increase in module production, percentage increase in module production over the previous year. So it's cumulative. And one of the surprising things here is that over that 12-year period, the average cumulative increase in production is 35%. That includes the annus horribilis here in 2012. And some remarkable things happened actually in this period 2008 to 2010. You see, in 2010, the rate of module production was 140% more than in the previous year. Absolutely incredible. So this period here I liken to the Klondike, where anybody with a shovel could get involved. And there were huge numbers of particularly thin film startups started in the United States and elsewhere. And obviously after the gold rush, we've had a bit of a sort out. These are the photovoltaic platforms. On the right-hand side here, we have concentrators. It was thought when solar cells were expensive that we could get around that by employing optics to focus light onto a small cell. The theory being that the optics and the tracking, etc., would be less expensive than the cells. Obviously, with what has happened over the last 2 or 3 years, this has made concentrators, or the financial case for concentrators, even in favourable locations around the world, rather dodgy. Work is still going on, companies still exist. Harmonics is a very good example. But the case for concentrators for photovoltaics is a lot weaker than it was several years ago. And then for flat panel modules, we have 3 generations. First generation is crystalline silicon, which still dominates the world market. It's still 90% of world production. In the UK, it's virtually 100% of what is being installed. Then we have thin film photovoltaics. There are 3 alternatives here: amorphous silicon, cadmium telluride, and CIGS, which is copper, indium, gallium diselenide. Of these 3, amorphous silicon was the first of these to be developed, but the efficiencies never really got beyond about 12%, and that's the champion cell, that's not a module. And the problem is that with the balance of systems overhead, you've really got to be at 10% more to be even anywhere near competitive. And although 1 or 2 of the companies in amorphous silicon, particularly Unisolar, produce very nice roofing tiles, that kind of product, most of the companies have been wiped out over the last 2 or 3 years, including Unisolar. CIGS is obviously a 4-element material, which means that it's actually quite difficult to manufacture. So although the record efficiencies are 20%, you get nowhere near that in terms of module production. And also, the phase diagram is so sensitive that if you move slightly away from the optimum composition, you quickly slide down in efficiency and performance. So companies, generally speaking, have found it very difficult to manufacture on a consistent basis. There is one company, the ex-Shell company, which is now called Frontier Solar, which is based in Japan. It used to be Shell Showa. They are doing okay. They've produced about 500 megawatts, but the only company that really is competitive. Against that, cadmium telluride thin film cadmium telluride is making a lot of progress. And in fact, most of the 10% remaining in the world market is produced by a company called First Solar. They produce thin film cadmium telluride with module efficiencies up to 14%. So we'll go into the case for cadmium telluride in a bit more detail. Then these third generation devices here, dye-sensitized solar cells, held out a lot of promise, but had fundamental problems with stability and lifetime, which have not been overcome. Most people, even in the R&D community, believe that these probably won't make it. The UK has put a lot of money into organic photovoltaics because we have a very strong research team in Cambridge and also Imperial College. Organic semiconductor materials were developed at Cambridge. They resulted in OLED displays. So they're using the same materials now for organic PV. They are making progress, but there are still problems with lifetime stability, etc. If we can overcome those problems, then they've got a lot of promise because they could be printed and they could be manufactured roll to roll. So that gives you an overview of the technologies. It's now down to, I think, at the moment, down to crystalline silicon and thin film cadmium telluride. Why is thin film cadmium telluride competitive? Well, the reason is that the total thickness of the device is, at worst, 10 microns. And actually, First Solar's devices are about 3 microns thickness. So fundamentally, it's going to be very cheap to produce. Also, there are much fewer steps in the manufacturing process compared with crystalline silicon. Crystalline silicon is typically 150 microns in thickness. So First Solar sorted out manufacturing problems. The company actually is managed by people who originated from Walmart, so they're very commercially savvy. And what they did was they sorted out a process and then started to replicate it around the world. In 2009, we're already over 1 gigawatt. I believe they're now well over 2 gigawatts. The thing about First Solar is that it's a public company. It's listed on NASDAQ, and hence its manufacturing costs are decipherable from the accounts. It was quite clear in 2009 that they were around about 70 cents a watt peak, which is the important metric. So what we saw was that in 2006, First Solar started to appear on the radar. This time Sharp and Q-Cells were the predominant companies. And then when they started to replicate their manufacturing process, they began to shoot up the ratings, so they're now 5th in 2007. And in 2008, they're 4th, and by 2009, they were the biggest company in the world. The Chinese, if we go back to this slide here, the Chinese are also beginning to appear here. You see Yingli here, JA Solar, Suntech. So a number of Chinese companies were coming through in this period also. The Chinese recognized that their costs of about $2 per watt and were not competitive with First Solar. And as a result, that they realized that their big problem was that they were competing with the microelectronics industry for the silicon wafers. and they didn't require the kind of quality that the microelectronics industry produced. So what they did was they got together and they produced a polysilicon plant. Polysilicon is the feedstock for crystalline silicon modules, and they put it next to a coal-fired power station because it's very energy intensive. And the cost of their polysilicon feedstock dropped by 80%. So that's the major reason why the Chinese are so competitive. Now, this is a graph of selling price against the size of the industry. And up to about 2009, this is around about the Klondike period, we had a nice progression that was people thought would be carried on into the future here. This bump here at 2008 was caused by a upturn in the microelectronics industry. So there was competition between solar and microelectronics at that point. The cost of polysilicon increased. And bearing in mind this is a log scale along here, that's quite a big bump. Then you can see what happened in 2009 when the polysilicon feedstock came through and first solar was still there. The price has absolutely plummeted and it's come off this trend which had existed for nearly 20 years. So I believe that First Solar were one of the principal causes of this huge drop in selling price. And as a result, of course, there was a big shakeout, and many of the companies that had been number one, including BP Solar, Q-Cells, a German company, Suntech, a Chinese company, all of these have been number one in the last 12 years, disappeared. So all of these have gone bust. And of course, the whole industry is now consolidated. So, where are the opportunities in terms of PV technology? Well, I think now module manufacture is highly competitive. We've seen a shakeout of the companies. There were 350 module manufacturers 3 years ago, and 200 of them have gone. So I see now opportunities in new manufacturing technologies such as solution and inkjet processing. There are opportunities for products that address the aesthetic barriers to deployment, including roof tiling and semi-transparent windows. And there's also opportunities, I believe, for batteries for energy storage with inverters. In the UK, we've had two outstanding successes in the last couple of years. One is the development of perovskite-based solar cells at Oxford University. In device evolution, we see each year maybe a 0.1 or a 0.2 or a 0.3% increase in efficiency. These guys at Oxford have gone 5% per annum over the last 2 years. These perovskites are now at 15.4%. They've come from nowhere, and they have a company, Oxford Photovoltaics, that has a very interesting proposition. I'll go into that in a second. And secondly, there's a company just north of Oxford called MSolve, who've developed a process for thin film modules for the interconnect. And again, I think they've got a very bright future. I'll just very briefly explain these. Now, perovskites could be used for conventional module manufacture, but because you can actually tune the color, if you make the absorber thin enough, they can be semi-transparent, and you can create power from windows. Now, because you're not absorbing all the light, clearly there's light getting through the window. Even if you're at, say, 5% efficiency, you would be generating 50 watts in a meter square. So if you consider the view outside this window here, you can see the scope for attractive looking windows creating power in tower blocks. And that's the market they seem to be addressing. It's a new market and should not be as competitive as module production. Photovoltaics produce a lot of current but very little voltage. So as a result, individual cells are strapped together in series to reduce the current and increase the voltage. That's quite easy in a crystalline silicon device because you just strap the wafers together. In a thin film device, it's much more difficult because you are depositing, let's say, the cadmium telluride over the whole of the module. And conventionally, if we look at the device structure, conventionally, this is the top contact, this is a transparent conducting oxide above the glass. You have to isolate cells by ablating down to the glass through the TCO, and then connect the TCO through to the top contact, so that the cells are then connected in series. Conventionally, in the manufacturing process, you scribe the TCO-coated glass down to the glass, then deposit 2 layers, then you take it out of the vacuum system, put it into another scribe machine, scribe down to the TCO, put it back, and then deposit the metal contact. The problem with that is you're in and out of vacuum, you're heating and cooling the module. It leads to huge inefficiencies in the thin film manufacturing process. So what MSolve have done is to create a machine with a head that has a laser, 2 inkjet printers, and a curing station all in one head. The lasers produce the scribes, and because the whole thing is in registration anyway, the 2 inkjets put in the insulator to isolate the cells, and the silver to connect the cells one to another. And this shows a scanning electron micrograph of just that. This is a scribe down to the glass to isolate the cells. This material here is the silver connecting one cell to the next. It works beautifully. And this is a picture of the kit. So the module goes on to this platen here after all the depositions are complete. And a machine of this size is capable of interconnecting 50 megawatts in a year, but crucially, after all the depositions have been complete. So, in essence, the manufacturing line in, say, a first solar plant, which is this long, can be reduced to this size by taking the interconnection offline. So, I think MSolve have a very bright future. So, just to conclude, now that we've got over the Klondike and the Annus horribilis, we're entering a new era for solar. Because the retail price in the United States are around about 60 cents a watt peak, we're now in many areas at grid parity, including California. We know in many parts of the world the fundamental economics are driving demand, not feed-in tariffs. This cost down curve is going to continue because it's such a competitive industry. And we believe that the industry globally is poised for massive growth still. And if Warren Buffett is putting in $5 billion, then there's got to be something in this. And last but not least, there are exciting developments taking place in the UK. Thank you.